Welcome back to Yale STEM Baddies. In this video, we are going to find the moment of inertia of a sphere, a solid sphere, that has uniform density. So we're going to say that the radius of this sphere in this problem is r, and it has mass m, and that mass is uniformly distributed throughout this sphere. So let's go ahead and start from first principles. The general equation of moments of inertia is the integral of r perpendicular squared dm. So that means that if we have a little slice or a little chunk of mass, we'll call that dm, this little chunk, then we need to find its perpendicular distance to the axis of rotation. And then we plug those two things into our integral, and that's how we find the moment of inertia. Well, what is the perpendicular distance to the axis of rotation? Well, in order to know that, we first have to specify the axis of rotation. So let's say in this problem that we will actually be rotating the sphere about the z-axis. So the z-axis is going to be the axis about which we are spinning. And then let's draw perpendicular then from this little chunk of mass to the z-axis. So there's that little perpendicular distance right there. Okay, perfect. So let's go ahead and start solving this problem using spherical coordinates. So recall that in spherical coordinates, we can represent a point. Instead of using Cartesian coordinates or these rectangular coordinates, we can represent a point using a different three values, which is going to be, primarily its absolute distance from the origin. We can maybe call that, I don't know, like little r. And then we also want to find the angle that red line makes with the z-axis. We can call this angle theta. And then if we project this point down into the xy plane, and then we, represent, we then draw a line to that point to the projection of that point in the xy plane. And then we also represent it with the angle that projected line makes with the x-axis, and we're going to call that angle phi or phi. That's going to be called the azimuthal angle. So we can use these three quantities, absolute distance from the origin, theta, and phi, to categorize where a point rests in space. Okay, so now knowing this about spherical coordinates, we're going to start manipulating our integral. So first of all, we know that our integral is going to take place in 3D. We're going to have, a three-dimensional problem here. So 3D, we have this perpendicular radius, and then instead of representing, our variable of integration as dm, I know that dm is also equal to density times volume. Density times our volume differential. But as we said in this problem, our sphere is uniform, so that means the volume throughout the sphere, the density throughout the sphere's volume is constant. So if rho, density, is constant, we can actually bring density outside of our integral. Okay, perfect. And then we're actually going to go ahead and represent this dv in terms of spherical coordinates. So instead of, dv as dx, dy, dz in Cartesian coordinates, we are going to represent it as, I don't know what order is best to do it in. Let's do it as dr, d theta, d phi. But then remember, because we're using non-standard coordinates, we also have to, we're not using Cartesian coordinates. We also have to scale, the guts of this integral by some Jacobian factor. And for spherical coordinates, hopefully you've just memorized at this point, or you can memorize, that this factor is equal to r squared sine theta, where r squared is, the distance of, any arbitrary point to, you know, the uh, the origin, and of course theta is that angle with respect to the z-axis. Okay, perfect. So then let's go ahead, and the last thing we need to do, there's actually two things we need to do. We also need to write down our bounds of integration, and then we have to do with this r perpendicular and represent r perpendicular in terms of our little, our spherical coordinates. So first of all, what are our bounds? So we have this sphere of big radius r, and let's say we take this little, chunk of mass here, and we then represent that chunk of mass's distance to the origin as, r. We have this z angle here as theta, and then we have its, projected angle, right here, this projected angle as phi. Sorry, drawing the wrong angle symbols here. Okay, so let's go ahead and think about the bounds. So for a sphere, we know that we want to integrate over all points that have radius between 0 and big R, right? Because that big R defines the end of the sphere. So our first big R is going to go from 0 to big R. Then what is our theta coordinates going to go between? Well, counterintuitively, you'd think it'd go from 0 to 2 pi, but I actually only want to pull that theta from between 0 and pi, 0 up here and pi down here. This vertical angle here, we only go this far. And a nice way to think about that is that if we then go that far, if we only go a half of a meridian, you can think about a globe. We're basically drawing a meridian on our sphere or our Earth. Then, if we have a half meridian on this side of the globe, we can then spin that by 2 pi in the azimuthal direction, and we can spin this half sphere all the way, we're spinning it all the way around the globe, and eventually we come back to where we started. And we only needed to start with a half meridian, and that then you can end up, if you spin that by 2 pi in the azimuthal direction, you can encompass an entire globe or sphere. I know that that's kind of nebulous, but basically you just need to picture cutting a circle out of a piece of paper, and then cutting that circle in half, so you have like a half wedge of a circle, and then you spin that half circle around in a full rotation around one axis, and then you've basically traced out an entire sphere using that half circle. So our theta variable goes between 0 and pi, and then our phi variable, this is where we want to we want to go 2 pi in the azimuthal direction, so that that half meridian traces out a whole sphere or a whole globe. Okay, perfect. And then how can we represent this, r perpendicular? What is that in terms of our spherical coordinates? Well, we have some sphere here. I'm going to just redraw it because our initial diagram is getting cluttered. We have some sphere here, and we have some little mass up here. Well, we know that r perpendicular is going to be the perpendicular distance from that little mass to the z-axis up there. We draw that perpendicular in, and then we also can draw in this distance is r perpendicular, this one right there. We also have r representing the distance to the origin. That's one of our coordinates. And then we also know that this angle here is, this is our vertical angle, this theta. So we see that these variables basically form a right triangle, and we can use a very simple relationship in terms of right triangles. We can see that the sine of that theta is equal to the opposite over the hypotenuse. So we can represent our perpendicular as r sine theta. Okay, perfect. So let's plug that into our integral expression now. So we have this density outside, 0 to 2 pi, 0 to pi, 0 to big R. And then instead of including r perpendicular squared, let's put in r perpendicular squared is r squared sine squared theta. Perfect. And then let's include then these variables, which is r squared sine theta. So remember, just make sure we keep track of what's squared and what's not. And then let's include our differentials. So dr, d theta, d phi. Okay, now let's combine our like terms that are stuck together with multiplication in that integral. So we're going to go ahead and combine those r squareds into an r to the power to the fourth. And then actually, I'm actually not going to combine those signs, and you'll see why. We could absolutely combine those signs to be sine cubed of theta, but I just want to leave it like that for now, and you'll see why later. But now you'll notice that we have these independent functions in this integral. These are just functions of r and functions of theta stuck together with multiplication. So we can actually break up this integral into three separate 1D integrals. So what is our phi integral? Well, there's no function in these guts with respect to phi. So phi is alone here. Our theta integral goes from 0 to pi, and we're left with sine squared of theta times sine of theta d theta. And then our r integral, it goes from 0 to r of r to the power of 4 dr. Okay, so I know that this integral and this integral are really, really simple. I can just do them now. So I know that the integral of d phi from 0 to 2 pi is just 2 pi, and the integral of r to the power 4 is 1/5 r to the power 5, evaluated at 0 to big R. Well, that's also easy. I can just go ahead and plug in an r here. That's all that is. And then I'm just left with this integral from 0 to pi of sine squared theta sine theta d theta. Okay, how do we go about tackling that last integral right here? Well, let's go ahead and use a trig identity. So, let me just write this better. So I know that sine squared plus cosine squared equals 1. So that means that sine squared equals 1 minus cosine squared. Pretty cool, right? So let's go ahead and make that substitution. So instead of sine squared, I'm going to put in 1 minus cosine squared times sine of theta d theta. Okay, very nice. And then let's go ahead and use a u substitution where we say that u equals cosine squared. Okay, perfect. So if we let u equal cosine squared, then I know that, or excuse me, that's not what I want to let u equal. I actually want to let u equal cosine. That's what I want u to equal, because if I take du d theta, I know that the derivative of cosine is negative sine of theta. And look, we have our sine of theta right there. So I know that du equals negative sine of theta d theta. Perfect. And then we can also then, move this negative sign over here. Okay, perfect. So we set up our u substitution. So I know that 1 minus, well, what is cosine squared? That's the same thing as u squared. And then I know that sine theta d theta, what is that equal to? That's negative du. And then let's also go ahead and plug in our limits into this equation. I know that cosine of 0 is, what is cosine of 0? Well, think about the unit circle. That's just 1. And then what is cosine of pi? Well, that is just going to be negative 1. So that's how we convert our limits of integration to u variables. Let's also just remember that this negative sign, we can take that outside of the integral. And then that also means that we can then just flip the limits of integration to be something a little bit more standard. So that negative just basically goes to flipping the limits of integration so that they're in chronological order or numerical order, you know what I'm trying to say. So then let's finally go ahead and just solve this super simple integral. The integral of 1 is u, and the integral of u squared is 1/3 u cubed. Remember, we're now evaluating at 1, so let's go ahead and plug in these evaluation limits. So this, and then we subtracted, evaluated at -1. -1 cubed. Okay, there's a lot of negative signs here. We want to be careful about our signs, but we're eventually just going to get, if we distribute this, if we distribute this negative here, we're going to get +1 plus 1/3 -1 to the power of 3. And this negative, remember, -1 cubed is this. So it looks like we're going to end up with these 1's combined to be 2, these 1/3 combined to be -2/3. We can, of course, write 2 as 6/3 minus 2/3. That's going to end up with 4/3. Wow, didn't that integral simplify nicely? So let's go ahead and plug in that result into this equation up here. This is what we have so far, and we just calculated that this whole integral was just nicely equal to 4/3. So are we done? Well, not really. We also want to get rid of this volume thing here. But we know in the case of uniform volume, it's just going to be, get rid of that density there. We know in case of uniform density, it's just going to be total mass over total volume. We already said the total mass of the sphere was represented by big M. And we, of course, also know from, middle school or early years of high school that the volume of a sphere is 4/3 pi r cubed. Okay, perfect. So let's plug in this for our density. Our density is big M over 4/3 pi r cubed. And then let's keep our 1/5 r to the 5 times 4/3. How cool is that? All right, I see that this 4/3 cancels. I see that, and I forgot a 2 pi, didn't I? Yeah, sorry, I forgot this 2 pi. We'll just add that on the end here. I see that this pi cancels, and I think this r cubed cancels, turning this into an r squared, because remember that r to the 5th over r to the 3 equals r squared. That's standard exponent rules. So now if we put this all together, we are left with this 2, this 1/5, this r squared, and this m. So we are left with 2/5 mr squared, and this indeed is the moment of inertia of a uniform sphere with an axis passing through its center of mass.